Everyone, welcome to Student Algorithm. So we have recently started the bit manipulation playlist where we'll be covering from basic to the advanced level topics in bit manipulation. So all you need to do is to watch our tutorials and follow our website where we'll be posting assignments for each video in our website studentalgorithm.in. So do visit our website for organized way of learning. So let's get into the video. So in this video we are going to explore four major topics: the story behind the compilation, conversions, binary to decimal, one's complement and two's complement, and bitwise operators. So first we discuss about the story behind the compilation. So in this story behind the compilation, what exactly happens after you run the high level language code? So the compiler converts high level code into machine code. Every operation in a computer is based on bits, zeros and ones. So what exactly happens is you have written the high level language code. High level language code is the code where you will be writing in a programming language such as Java, C++ or Kotlin or etc. Whatever the programming language you will be writing, that programming language cannot be understood by the machine. So the machine just understands zeros and ones. So our job is to convert these high level code to the zeros and ones. So how does exactly this happens? First, the source code. We'll be writing source code. Source code is nothing but the high level programming language. This will be this will be going through the pre-processing state. In pre-processing state, what exactly happens is before compilation, it must ready. The code or the program should be ready before compilation. So that process will be taking care by the pre-processing process, where what exactly it does is, for example, it's taken hashtag include stdio.h header file in C language. What pre-processing process will be doing is it will be removing hashtag include stdio.h and just renaming as stdio.h. So this is done by pre-processing process. And also let's take the define example as well. In hashtag define, pi is equals to 3.14. Whatever the pi, for suppose I have written pi over here, pi is equals to, I have used pi in some instruction in a program, in certain line in a program, that pi is converted into 3.14. This all can done by the pre-processing. And then compilation in the sense it will be checking where any errors happens or errors are there in the high level language code. If the compilation is successful, if you don't have any errors, if the compilation is successful, it will be converted into the assembly level language. Assembly level language is a language where what exactly happens is it's like English kind of language. You will be having some instructions like move, add, sum, difference, mult, etc. So this data will be stored in the registers. The registers transfers takes place in the assembly language. So it's kind of English level language, remember up to that. And then after converting into the assembly level language, it will be converted into the machine code. Machine code will be in the form of the zeros and ones. So now let's get what exactly happened behind the compilation. So first let's consider the source code, where we have written int a is equals to 10, int b is equals to 5, int c is equals to a plus b, and we are printing c. So this is just basic code of the high level language. So what exactly happens behind this code? So let's consider RAM over here first. So RAM is a memory space. It's a what exactly it does is it creates some process states. Process is nothing but this program in execution is called as process. RAM creates the process spaces. These process spaces contains number of processes. Like it contains so many number of processes. So each process performs certain operation and it executes. Like in this, let's consider this process. In this process, we have stored variables a, b, c. So in a we have 10, in b we have 5. So these are the variables we have stored in one process. So RAM will be creating certain process, number of process. So we are looking what happens exactly in one process. So in one process we'll be having different variables. So these variables will be performing certain operation. To perform some operations, we require what? We require ALU, arithmetic and logical unit. So we see the mechanism how it works. First, it will be taking input from the input registers. ALU will be taking the input from the input registers through data bus. Data bus is like it transfers the data. I mean, it is like a transport mechanism where A comma B will be going through the input registers and it perform certain operation. So here we have declared A is equals to 10, B is equals to 5 and C is equals to A plus B. So the operation performed is A plus B. So in this ALU operation, it performs A plus B. That means it performs 10 plus 5, right? So after performing certain operation, it will be producing output through the output register to the variable, output variable. We have stored this A plus B in C. So it will be moving through the output register to the C through data bus again. So what exactly happens again? The RAM will be creating different number of processes. In each processes, the different variables will be stored. The ALU will be taking the input from the input registers and then perform certain operations and produce output through the output registers. So this is exactly what happens behind the compilation. Now let's move into these conversions, where we will be converting decimal to binary and binary to decimal. Like okay. So in these conversions, we are converting decimal to binary and binary to decimal. So in decimal number, what unique numbers will be having? We will be having from 0 to 9. That will be equals to 10. Total number of digits include 0 as well. 1 to 9 plus 0 will be 10 digits. And in binary, we will be having 2. 1 comma 0, then 2. The total number of digits present in the decimal is 10 and the total number of digits present in the binary is 2. So now we will be converting the decimal to the binary. So how we will be doing that? Let's look. So first we'll take an example of 17. What we will be doing is we will be dividing 17. So if we divide 17, the quotient will be 8 and the remainder will be 1. So then again you have to divide 8 by 2, the quotient will be 4 and the remainder will be 0. Again you need to divide it by 2, it will be 2 and 0. Again you need to divide it by 2, it will be 1 and 0. Again you need to divide it by 2, 0 and 1. If you further divide it by 2, it will be getting 0 quotient and 0 remainder, no need to divide further. If you get 0, you just stop it. So after dividing, so you will be getting some reminders, right, in the form of 0 and 1. So you need to write from reverse, like 1 0 0 0 1 is your binary representation of 17. Now let's look how this 17 is converted into the binary. So firstly we have took 17, right? So what we need to do is the nearest value of 17, the nearest value of 2 power n, which is smaller than 17, we need to check, right? So from first we'll check. Okay, so now we'll check 1 comma 2. So 1 2 which is nearest and which is smallest, 2. Again we need to check 2 comma 4, which is nearest and smallest. 2 power n value for the 17, it will be 4. Again we need to check 4 and 8, it will be 8. Again we need to check 8 comma 16, it will be 16. Again we need to check 16 comma 32. Here 32 is larger than 17, so we should not take 32, we should take 16, right? Got? Then we need to put 1 over here. Then we need to subtract it. How much we got? 17 minus 16, that will be equals to 1, right? So again we need to check the same process. It should be greater than and nearest value to the 2 power n. So here we have 1. So we need to put 1 over here, and remaining we need to put zeros between. So this is the simplest way to convert binary binary numbers from the decimal. Instead of doing all this thing, we can easily convert any given number to the binary representation using this technique, right? Now let's move into the converting decimal number to the binary number. We have powers of 2 over here, right? As we see, we have powers of 2. As we have the power of 2, let's consider the 17 number. We have power 0, 1, 2, 3, 4, and then 5, 6, right? So whatever ones you have, like you have 1 over here, 1 over here. So you need to multiply this with the 2 power. Like for suppose you have 0, right? We have to multiply 1 into 2 power 0 plus 0 into 2 power 1, it will be 0, of course, I am directly writing 0, plus 2 into 2, 0 into 2 power 2 will be 0, 0 into 2 power 3 will be 0, 1 into, next we have 1 into 2 power 4, right, which is equals to 16 plus 0 plus 0 plus 0 plus 1, which will be equals to 17, right? This is how you convert your binary number to the decimal number. So all you need to do is what? You need to take the powers over here 0, 1, 2, 3, 4. Wherever the 1 here you can see, you need to multiply direct, like 2 power 0 plus wherever at whatever position you will be seeing 1, then you need to directly add those. For the shortcut method, 2 power 0 plus 2 power 4, you will be getting the 17 as answer. So this is all about conversion of binary number to the decimal. Now let's look into another topic, ones complement and twos complement. We will be using ones complement and twos complement to convert to represent it in form of the negative numbers. We have written 17, right? We have written 17 in a binary representation. What about minus 17? How we can represent the minus 17, right? This is all what we need to learn. Generally, the computers will be having the 32-bit architecture where every number will be storing in the 32 bits. Like for suppose if we want to store 1, it will be storing in 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and the last one. Here 0, 1 till 31. So every number will be storing in the form of 32 if it is a 32-bit architecture. To understand this 32-bit architecture is difficult to write all the stuff, so we'll be discussing it in the form of 8-bit architecture. So we'll be going through 8-bit architecture here. So now let's get into the video. So firstly, just a minute, right? Firstly, we have 1, 0, 1, 0, and all these things, right? First, we need to convert the number into the negative number. First, we need to convert this into the ones complement. Ones complement is nothing but if you have the 1, we need to convert it into the 0. If you have 0, we need to convert it into 1. So you need to flip the bits, right? So for example, if you have x can be converted into 1 minus x. Like for suppose we have the two options, right? If you consider x equals to 0, 0 and x equals to 1, then 0 equals to 1 minus 0, and then 1 equals to 1 minus 1, which is equals to 1, which is equals to 0. That means if we have 0, you need to convert it into 1. If we have 1, you need to convert it into 0. This is the basic concept of one's complement. You have 1, you convert it into 0. You have 0, you need to convert it into 1. You have 0, 1, 0 converted to 1, 1 converted into 0, 0 converted into 1, 0 converted into 1, 0 converted into 1. This is all about one's complement. Now let's move to the 2's complement. In 2's complement, nothing you need to do. You need to perform, just you need to add 1 to the 1's complement. Like you have 0, 1, which will be 1, of course. 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 0. Then you will be 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1. So now, as we discussed the 8-bit architecture, you will be having the 8 columns over here, right? 2, 3, right. So whatever the last component is present, that will be calling as MSB. MSB is nothing but most significant bit. So the last whatever the bit is there, that will be considered as MSB. If it is 0, then it is positive number. If it is 1, if the most significant bit is 1, then it will be converted into the negative number. So with the help of the MSB, we can convert positive to negative and negative to positive. So now let's see what exactly happens over here, right? So first we took 1, we'll be converting this number to decimal. Okay, directly we need to convert. Then we'll be adding 1, 2 plus 2 plus 4 plus 8 plus, we should not take 16 because we have 0 over here, plus 32 plus 64 minus 128. So that will be equals to minus 70. So what we have done, we have converted 17 to minus 17 using 1's complement and 2's complement. So next we'll be moving to the bitwise operators. There are majorly 6 bitwise operators. So first we'll discuss about 3: AND, OR and XOR operator. So first we look into AND operator. AND operator says if you have both bits 1, then it will be giving 1. If anything you have, like any of the bit will be 0, then the result will be 0. So this is all about your AND operation. So we have 22 in a binary form, 28 in a binary form. Will be performing AND operation for this bits. So 0, 0 will be 0, 1, 0 will be 0. Why? Because we don't have 1. If you have 0 in any of the bits, then that will be resulting to the 0. You have 1, 0, 0, 1, 1. Here we have both bits as 1, so it will be resulting to the 1. You have 0, 1, 0, 1, 1. Again it will be 1, right? So this is all about AND operator. Now let's move to the OR operator, where if we have at least one in one of the operation, then the result will be 1. You have 0, 0. You don't have 1 in 22 and this bit, then the result will be 0. Then 1, 0. We have 1 over here. 1 over here, so the result will be 1. Then 1, 1. Of course we have to 1 or 1 will be equals to 1. 0 or 1 will be equals to 1. 1 or 1 also equals to 1. Now let's move to the XOR operator. XOR operator says if you have the same numbers, like you have the 0 comma 0 or 1 comma 1, it results to 0. If you have the same numbers, the answer will be equals to the 0. Like you have the same number 0 0, then it will be 0 1 0. You have the different bits, then 1 1 1. You have 0, same bits. You have 0 1, different bits, so the result will be 1. You have the same bits 1 1 here, then the result will be 0. This is all about the XOR operation. Now let's move to the now let's move to the NOT, left shift and right shift. So in NOT operation, we have already discussed uh, ones complement, right? So in ones complement, NOT operation is nothing but this. We'll be representing it in the form of negation, like negation 17. We'll be converting 1 to 0 or 0 to 1. Like if you have 1, we'll be converting into 0. If you have 0, we'll be converting into the 1. This is all about the negation. Next we'll be moving about the left shift and right shift. So first let's talk about the left shift. So here left shift is nothing but whatever the bits you have. Like let's take this is the minus 89. So whatever the bits you have, you will be moving to the left, like to the position. See, this is the 0 position. This position 0 position is moved to 1, 1 position moved to 2, 2 position moved to 3, 3 position to move to 4. So this exactly happens in the left shift. So the remaining space will be filled with 0. Similarly, in right logical shift, what happens is this 1 position will be shifted to 1. This 1 position will be shifted to 0 position, and second position shifted to 1 position, and third position shifted to fourth position shifted to third position. It will be shifting to the right, completely right. So the 1 will be shifted here, 1 will be shifted here, 0 is shifted here, 0 is shifted here, 1 shifted here, and 0 shifted here, and 1 shifted here. The remaining space is filled with 0. This is all about the left shift and right shift. So now let's revise what we have discussed entirely. So in bit manipulation playlist, we have discussed the story behind the compilation, wait for source code, then pre-processing, then compilation, assembly and machine code will be converted. The process will be converted from the high level language to the machine code to execute. And then the conversions we have discussed, how to convert decimal to binary and binary to decimal. To convert decimal to binary, we just divide it by 2 and we just store the reminders. From the binary to decimal, what we do is we just multiply each bit by 2 power n and sum the values. And then we will be converting ones complement and twos complement. Why we require the ones complement and twos complement is to convert the positive numbers to the negative numbers. I mean, to represent the signed numbers, we require the ones complement and twos complement. And what about the bitwise operators? We discussed about the AND operator, OR operator, and XOR operator, negation, left shift, and right shift. So in next video, we'll be going to explore the bit manipulation tricks. So solve the assignments. So in the assignment, you will be having some unique questions. So try to solve them so that you can improve your problem. Definitely solve the assignments. I suggest you to solve the assignments to get whatever you solved, or else just look into it. So next video we are going to explore the bit manipulation tricks, but you need to definitely solve the assignment question. The assignment will be provided in our website as well as in the description. So do visit our website and progress your learning journey. So this is all about this video. In next video we're gonna discuss about the bit